But let's get started. So, as usual, I wanted to start with a little note about today, March 17 in CS history. 31 years ago today, John Bacchus passed away at 82 years old, and he was a computer scientist of some note. He was a winner of the National Science Medal and the ACM Turing Award and various other awards. He led the team that developed Fortran, which was the first really widely used programming language. Also, if you've taken a compilers class, you no doubt learned BNF as a way to describe context-free grammars, and he's the B in BNF. And since this is a networking class, it's worth noting that parts of many of the protocols that we use are defined using BNF. For example, the specification for HTTP, the protocol underlying the web, uses it heavily. Here's how dates are represented in HTTP in BNF form. So, not a bad legacy. Back to 168. Let's take a quick look at sort of where we are in the course. We started out by talking about some foundations and principles behind the internet, and those were things like packet switching and end-to-end principle. We talked about the domain structure of the internet and routing within and between those domains. Then we've done a pretty deep dive on IP and TCP. We've looked at what those packets are actually composed of at L3 and L4. We've looked at the actual bits on the wire and what they're for. And we've seen how to make an unreliable network act like a reliable one. And all that is sort of, establishing foundations. And today we start at least a couple of lectures that start to have a bit more focus on the user. And specifically, we're going to start by talking about the domain name system, or DNS. As part of our remote learning, the plan is to break up the DNS material into a number of separate videos, which we'll post individually. And then we'll have some online interaction starting with Piazza and online office hours, and we'll kind of see where things go from there. So here's the outline for all of the DNS-related videos. We're going to start out with sort of an overview of the ideas and how name lookup works at a very high level. And then we'll get into some of the details that support DNS's core mission. We'll talk a bit about the API that you can use to interact with it, about the servers that support it, and about the protocol itself. We'll talk about the two most important types of information in DNS, the A and NS records. And then we'll talk a bit about how domain names are actually created. The next video will then go much broader and look at other use cases for DNS than its core one, and the various record types involved. Then we will have a little case study that looks at how Minecraft uses DNS to solve a real-world problem. Then we'll discuss availability, scalability, and performance of DNS. And we will finish off our discussion of DNS with some musings on the subject of DNS, sort of from a skeptical standpoint. So with that, I'll conclude this introduction, and you can move on to the overview. So thinking back to the early internet, the three killer apps were basically remote terminal, that is from a local machine. You could log into a machine somewhere else. This is like SSH is today. At the time, it was a protocol called Telnet, and you could do Telnet and then the remote host address. File transfer, pretty self-explanatory. You did it with a command called FTP, which used the file transfer protocol. And so on the command line, you could do FTP and then the remote host address. And then email, where you want to send or receive messages to or from a user on a remote machine. And you could do that using the command mail. And, numerical host addresses were not very nice for humans. Nobody wanted to type telnet 46.0.0.10, for example. But that's all we've talked about so far, these numeric addresses. So the solution was to create an address book of host names and their addresses. And this was maintained by Elizabeth Jocelyn Jake Feinler at the Network Information Center at SRI. SRI, of course, being one of the first two nodes of the sort of nascent internet. So if you wanted a host name, then you phoned Jake Feinler and she'd enter it in a database that she kept. And originally, this was a human-readable file, basically. It looked something like this at the beginning of 1974. There were 85 or so hosts, and I want you to take a look at the addresses and notice that they are not IP addresses. They're really just a single byte. Also want to point out that UC Berkeley is here with address 98, and I think these lists were basically sent out as pretty much part of a newsletter. So eventually, this sort of transitioned to a standardized machine-readable format, commonly known as hosts.txt. And so everyone periodically used FTP to fetch hosts.txt from the NIC. So in 1983, the standardized hosts.txt file looked something like this. There were now 480 hosts or so. I haven't shown them all here. But notice that they now have IP addresses. And so there were a whole bunch of these 10 ones, which are ones that had been migrated from the earlier ARPANET addresses. Again, notice that UC Berkeley is here. But at this point, Berkeley also had its own whole network, this 46 network. Notice that this is a Class A network. This is like a /8. That's a lot of address space. By 1986, they no longer had 46 and instead had transitioned to 128.32, which is a Class B network. And Berkeley actually still has this /16. So with this hosts file, you could type telnet UCBVAX, for example, and UCBVAX got looked up in the hosts file and it opened a connection to 46.0.0.10, the corresponding address. And this is a whole lot nicer than having to type in and remember the addresses yourself. However, this arrangement was still not ideal. First of all, it was sort of an increasing amount of work for Jake Feinler and her team. It was also an increasing amount of data transfer. As the network grows, as you get more hosts, first of all, the file size increases. But secondly, the number of hosts fetching it increases. And the frequency with which you need to fetch it in order to remain up to date increases. And so, in the absolute best case, this is quadratic. And there were starting to be a lot more hosts. The early internet had been sort of characterized by a few mini computers hooked up together. But we were entering sort of the age of the workstation computer here. And so there were suddenly being a lot of hosts that wanted to get on the internet. You've also got this problem where longer transfers are more likely to fail. And so you may end up with partial hosts files until you download the updated version a few days later. So in short, the centralized administration was becoming to be burdensome, and it was clear that it was going to be even more so in the future. And it was also sort of, this centralized, NIC-centric focus was sort of counter to the sort of open and decentralized path that the internet was on. And also the centralized distribution of the increasingly large file was also looking like bad news. So DNS, or the Domain Name System, was developed to confront the problems being faced here. It was developed by Paul Makapetris in 1983, and he was actually sort of given the task of pulling together several different proposals for such a system into a final one. He kind of just developed his own one instead, and without much change, that's the one that we still use today. So what are the goals of this system? Well, first of all, the primary purpose is to map from human-friendly names to IP addresses. While it does this, it needs to be able to deal with scale. There are going to be lots of hosts and names. They probably didn't foresee this at the time, but today there are about 360 million domain names. There's also going to be a lot of lookups, a lot of people who want to map a name to an address. And there's going to be a lot of updates. We don't want to have a bottleneck like having to make a phone call to the NIC in order to add a new domain name. We also want the system to be highly available. We don't want a single point of failure. For example, in the old scheme, if the NIC's FTP server went down, then you wouldn't have any way to get an updated hosts.txt file. And we want the system to perform well because, lots of communication is going to start with a name lookup. So, how do you solve problems like these? Well, we do it the same way we solve many similar problems in computer science, which is with hierarchy, or in this case, with three intertwined hierarchies. So, the first hierarchy is that the names themselves form a hierarchy. You can take any node and you just sort of trace it up towards the root, and you get a name. Note that intermediate nodes make valid names too. For example, eeks.berkeley.edu is a valid name. You don't need to go all the way down to the leaf. Secondly, authority is hierarchical. You have this way of sort of delegating authority. For example, EduCause, which is, I believe, a non-profit, is sort of responsible for all .edu domains, but then Berkeley is responsible for .berkeley.edu domains. And finally, the infrastructure itself forms a hierarchy. The infrastructure is not just a single server that knows all the names. It's a hierarchy of name servers which all know about parts of the hierarchy. So, for example, a.eduservers.net is a name server that knows about the name servers for all .edu domains. adns1.berkeley.edu is a name server that knows about various stuff below berkeley.edu. And Eeks has its own name server, ns.eeks.berkeley, which knows about stuff at or below eeks.berkeley.edu. And note that adns1.berkeley doesn't know anything about the stuff that ns.mount Holyoke knows. So looking at the bigger picture here, we start with a root, which I didn't put in the previous diagrams. And so the DNS root is controlled by ICANN. Below that, we have these top-level domains, or TLDs. And there's a whole bunch of them. And these are controlled by various different organizations. Like I mentioned, .edu is controlled by EduCause. VeriSign controls .net and .com. There are these country code ones for all the countries, and those are controlled by some organization that's part of that country, and so on and so on. And so there's about 1,500 top-level domains today. And below that, we have, all the other domains, which are controlled by many, many different organizations. So we have this concept of a zone. And so a zone corresponds to an administrative authority responsible for a contiguous portion of the hierarchy. For example, the name server, adns1.berkeley.edu, is responsible for berkeley.edu and pink.ischool.berkeley.edu and www.berkeley.edu. But then Berkeley has delegated the authority for Eeks and below to a different name server. So a different name server serves rise.eeks.berkeley. And this means that you kind of have a choice about whether and where you want to delegate authority of children. And it basically means that Eeks doesn't need to coordinate with main campus IT in order to make domain names for Eeks machines. Okay, so how do lookups actually work? Well, we've got this iterative resolution process where basically we start with the root name server, we ask it for the name we want. If it has an answer, then we're done. Otherwise, it'll direct us to the next name server that we should ask. And then we just repeat this process until we actually get the answer we want. So let's do an example. Let's look up or resolve repo.eeks.berkeley.edu. So we ask the root server a.rootservers.net for repo.eeks. Now, it's not going to know the answer to that, but because it's a root server, it knows all the top-level domain name servers. And so it's going to tell us to ask one of those responsible for .edu domains. So we ask a.eduservers.net for repo.eeks, and it doesn't know either, but it knows about berkeley.edu. And so it knows a name server that we should ask. And so we ask that name server, adns1.berkeley.edu. And it doesn't know either, but it knows that we should ask ns.eeks.berkeley.edu. So we ask ns.eeks, and it actually tells us the answer that we're looking for. So this may be kind of obvious, but I wanted to make a little side note. We already walked through how the domains are broken down into top-level domains and so on, but that was really talking about the names themselves. But there's also this sort of parallel hierarchy for the infrastructure too, the actual name servers. And so people often classify the name servers by which part of the hierarchy they're in. So at the top, the root server knows about top-level domain servers, and then we have top-level domain servers which know about that particular top-level domain. Like there are servers that know about .edu, like berkeley.edu and Mount Holyoke.edu. But they don't know anything about like eeks.berkeley.edu. And then we have authoritative servers, and these are ones that actually like do the name to IP mapping. They know about the stuff that's in their zone. Okay, so back to the lookup process here. This has raised three important questions. And so the first one is, who actually does this multi-step lookup process? And originally, back in the 80s, it was likely that a host did this directly. That is, the host would query the root server, get the response back, query the top-level domain server, then query the authoritative servers, and eventually get the answer. Today, things work a little bit differently. We usually have what's called a resolving name server. And so basically, the host queries it, and then it makes the same sort of, iterative queries that the host would have made in the past, and then it returns the result back to the host. And so this is called a recursive query, and these are the same non-recursive or iterative queries that we've had the whole time. So to go on a little rant here, I've never liked the name recursive. If it were a recursive query, I would think everybody would do the same thing. So like the host would query this server, which would query this one, which would query this one, and this one, and this one, and then the replies would go back the same way, and then you would have gotten the response. And I mean, this works logically, but practically speaking, this doesn't actually end up happening because these servers along the bottom generally don't support recursive queries. Like recursive queries take them more work, and they're all really busy. And in particular, like the root servers don't support recursive queries. You could also imagine some scenario like this. Maybe the Berkeley name servers, for whatever reason, had been configured to support recursive queries. And so you could imagine that you might get some sort of combination where you've got a recursive query here, and you've got iterative queries here, and then you've got another recursive query here. And so, I mean, again, this works logically, but practically speaking, this never happens. You always get sort of that first scenario, basically, where the resolving server, which is generally provided by your ISP, like in this case, a Comcast server, is the one that's responsible for doing all their iterative queries. So, just to finish up my rant here, I really think this should be called a delegated query, right? Because if it's, just this one sort of delegated query and then it's all iterative queries after that, the name recursive just doesn't make sense to me. Okay, rant over. So when a server gets a request for a normal, non-recursive query, if the server knows the answer, then it returns it, right? If it doesn't, then it returns a reference for the next server to query. When a server gets a request for a recursive query, then if the server knows the answer, again, it returns it. And in theory, it could perform a recursive query on the next server, but it's more likely that this server does the iterative process itself. And so that would be, truly recursive. This one would be, not really recursive. And it's even more likely that it's just going to return an error saying that it doesn't support recursion. Because usually it's only these specialized resolving servers that actually support recursive queries. Like I said, these servers are often provided by your ISP, and they generally aren't authoritative for any domain. You know, they don't have specific named IP mappings that they're responsible for. They're really only used for lookups. So going back to, you know, our sort of classification of types of DNS server, we could add, you know, the resolving DNS servers, though it's worth noting, really, these aren't really part of the hierarchy in the same way as the other ones are. And so that answers our first question of who actually does the lookup process. A host can do it, but it probably delegates it to a resolving DNS server. And so that leads to our second question, which is, how do I know the address of my resolving DNS server? And one possibility is that you do it manually. A more likely possibility is that you use DHCP, or the Dynamic Host Configuration Protocol, which we're going to talk about in a future lecture. But I do want to point out that you can have more than one name server. You know, depending on the OS and the configuration, it may cycle through them all, or it may switch to a later one if an earlier one fails, or something like that. Okay, so this could be manual, but it's probably through DHCP. And so that leads us to our third question, which is, how does anyone know the address of the root DNS server? But before I get into that, I have to come clean about a little fib I've been making. I've been talking pretty much like there's one root name server, and like Berkeley had one name server, and so on. And I want to point out that this is actually already somewhat resistant, or rather resilient to failure. You know, Berkeley's name server could go down, and that wouldn't affect UCLA, for example. But actually, every zone always has at least two name servers, replicas of each other. There's no real reason why this has to be true for like some strong technical or theoretical reason. It's really just true because the IETF said so, and people follow what they say. So, you know, the main Berkeley zone has at least these three name servers, ADNS 1, 2, and 3. EDU has 13 name servers at least. You know, a.eduservers.net and b.eduservers.net and so on. And the root also has 13. It actually has more, and we'll come back to this later. Okay, so how does anyone know the address of a root DNS server? So, you know, we know that it's named a.rootservers.net or b.rootservers.net and so on, but like, where do you look that up to actually find its IP address, right? We've got like a bit of a chicken and egg problem here. And so there are multiple ways that you might do this, but a pretty decent solution isn't too complicated, and is generally how it's done. And basically the program that does the name resolution ships with the root server IP addresses like hard-coded or in a configuration file that were current when the program was shipped. And basically the program tries to query each of those pre-configured addresses until it finds one that works, and then it asks for an up-to-date list. And this is called a priming query. And this works as long as at least one of the pre-configured ones still works. So, how does one know the address of a DNS root server? Pre-configured addresses, which are then used to get updated ones through the process of priming. So a final note on lookup is, remember that hosts.txt file from the pre-DNS world? It actually still exists on systems today. But there's usually not much in it. But you could put things in it if you wanted to, for example, override how a particular domain name gets resolved. So continuing our discussion of DNS, I thought we should get into some of the details. And so we'll talk some about the APIs, we'll talk about the servers, we'll talk about the DNS protocol itself, and then we will finish up by talking about how a domain is born. All right, so the usual API functions are get host by name, which you just pass a domain name and you get a result back, which you can use to get the address. This is really old. It's been deprecated for many years. I think maybe like almost 20 years. It's super common in real code anyway. It's really big drawback, and the reason that it's been deprecated for so long is really because it only supports IP4. It doesn't support IPv6. So its replacement, more or less, is this function getAttrinfo. You can pass it the name, and then it has a couple other parameters which you don't necessarily need to pass in, and then you pass in a pointer to a value that gets the result. So this is modern. It's not limited to IP4, and both of these are available in both, like the C libraries on Unix-like systems and on Windows, and they're also both available in the Python socket module. Usually, the implementations of these don't know how to make iterative queries. They only know how to make that, first query to a resolving DNS server. So talking a little bit about servers, the gold standard DNS server, which I think is also far and away the most popular one, is a server called Bind. And Bind was also actually the first DNS server written for Unix, and it was written by 4 Berkeley grad students in 1983, like the same year as the DNS RFC was written. And so there's a paper from back then by its original authors about Bind. So it stands for Berkeley Internet Name Domain Server. I always thought this was a super awkward name. Like, why not call it Berkeley Internet Name Daemon? So, side note, daemons. Some of you may already know this. But for those of you that don't, many network server processes are called daemons. Sometimes it's pronounced daemon. Both seem to be pretty well accepted. The main program of Bind, for example, is called named. That's not named, it's named daemon. And, if you're familiar with SSH, the SSH server is usually called SSHD. This isn't strictly just for network servers. It's really just processes that are sometimes referred to as background or non-interactive processes, so that's sort of misleading. Like a name server is certainly interactive. You send it requests and it sends you replies, but it's not generally run or used like directly from the command line as part of like an interactive session. So sort of roughly, and this is sort of a vague term, a daemon is a server process. They're generally long-lived, and they're generally communicated with through some sort of an inter-process communication or network mechanism. The equivalent programs in the Windows world are generally just called services. So why daemon? And this goes back to, thought experiments, at least as far back as Descartes. And so he did this thought experiment that had this daemon, this entity, which was basically working tirelessly to deceive you about like the nature of the world, about reality. And so Maxwell's daemon is one that was used in a thought experiment in physics. And it was maybe this one which was actually the direct inspiration for daemons in computing. Maxwell's daemon sorted molecules in such a way as to defeat the second law of thermodynamics. And so, really in a thought experiment, it's just some entity that has some particular job that it just keeps doing. And so, I think in computing, the analogy is really just that like this entity kind of works in the background to do some ongoing task. So given that it was Berkeley students that wrote Bind, and Berkeley has been involved in DNS since the very beginning, perhaps it should not be too surprising that berkeley.edu is actually the oldest edu domain on the internet. All right, so let's talk a little bit about the DNS protocol. It is a client-server design. The client is often a user host, but it could be another server, like in the case of recursive queries, right? It's like that second server that's actually acting as a client for the remaining servers. So the client sends a query, the server sends a response. So the server typically listens on the well-known UDP port 53. And so, we spent a lot of time talking about TCP. And so why UDP? Why is UDP the right fit for DNS? And so one answer is that it saves, an RTT for the TCP connection establishment, right? Also, TCP requires servers to keep state per connection. And there are potentially lots of connections, especially like if you think about like the root servers. And just in general, there's no real need for that sort of ordered stream abstraction that you get with TCP. Like for these quick queries and responses, like a single packet is often just fine. And so you may be saying, but like, wait, UDP isn't reliable, so what if packets are dropped? And basically, DNS deals with that just with this sort of simple timeout and retry mechanism. It varies from OS to OS. It can be fairly slow. Some OSs are much more clever, like if you have multiple DNS servers set up, it will, like when it retries, it will send it to both of them. And to try to maximize its chances of getting a reply quickly. Others are not nearly so clever. So again, it really just sort of varies system to system. But it can be fairly slow. Like it can be on the order of like seconds if a packet gets dropped. But you have to keep in mind like your DNS resolving server is often provided by your ISP, so it's generally pretty close to you, and you're generally pretty well provisioned for that. So the chances of losing a packet between you and that resolving server are pretty low. And later we'll kind of see why that's often good enough. So some DNS servers also use TCP port 53. It's not usually used for normal queries. It's primarily used for what are called zone transfers, which is when you're replicating the name database. And, kind of the notion there is that, this is much more data than like a normal query, right? If you're copying the entire database. And with this, larger amount of data, the three-way handshake likely becomes negligible. And sort of the reliability and ordering that TCP provides you becomes important for doing these big transfers. We'll talk some more later about some additional variants of the protocol. So all messages share the same basic format. The messages can be either a query or a response, and this is determined by a QR bit in the header. Queries can also theoretically be of several different types. There's the iQuery, but this was obsoleted in 2002. The RFC that obsoleted had this note that iQuery has not been generally implemented and has usually been operationally disabled where it has been implemented. So not extremely successful. There's also the status type, which was never really defined. There was a proposed standard in 2001, which, nobody got around to trying to define until 18 years after DNS was defined. And this proposal was not even accepted. And so it's really just this query type, which is used for basically everything. So we're kind of going to just ignore the different types of queries. There's also a bit in the header that determines whether recursion is desired. It's how you express that you want a server to do a recursive lookup. If you're interested in more details in the actual protocol, you can either see the text or look at the RFCs. So the actual data that's stored and transferred in DNS is held in resource records. And resource records are basically a tuple. And the first value in the tuple is the type. And there are many different types of records. And if you remember that the primary goal of DNS is to map human-friendly names to IP addresses, we need two types of record to do that. And the first one are A records, which are address records. And the second one is NS records, which are records telling about another name server. We'll talk about some more types later. The name field of the tuple is basically just the name associated with the record. For example, in A records, this is the host name of interest, like www.google.com. The value is the value associated with the record. For A records, this is the IP for address associated with the name. The TTL is how long in seconds this record is valid for. When I write out tuples going forward, I may omit this value. And then there's the class. And basically the idea here is that DNS can actually be used to store, information for different types of networks besides just the internet. And so the class specifies which network type you're talking about. I don't think this was ever actually used very much, so class is almost always equals internet. In this particular class, it will always be that, so I'm just going to ignore it moving forward. So let's do another example, this time with the actual protocol in mind. And this is actually based on a real query that I did by hand. So we start by querying a root server requesting the A record for ischool.berkeley.edu. We want to know its IP address. And the server sends back this NS record. And of course, this is not what we asked for. But it's basically its way of saying, I don't know the answer to what you want, but here's a name server that knows something about domain names ending in .edu. So now we know about this other name server to ask. The server also sends back an A record for k.eduservers.net. This is in the same packet. And it didn't really need to do this. We didn't ask for it, but it's useful, right? Like assuming that we want to continue with our query, we may well need this IP address. This may have been our next query anyway if it hadn't included the answer already. So this is called an additional record. Also, I only wrote one NS record here, but in the same packet, it also returned a bunch of other name servers in random order. And so that way I can try other ones if the first one doesn't work or something. And if every client starts by just asking the first one that it gets, then the load will get kind of spread evenly across them. So next, we're going to query that new name server that we found out about, k.eduservers, requesting the A record for ischool.berkeley.edu. And that name server is going to send us back this NS record. And again, this isn't what we asked for, but, basically it's saying, here's a name server that knows about things ending in berkeley.edu. And again, it's also going to return an A record for that new server so that we know the IP address of that server, which we're going to use to query it, asking it the same question. We want the A record for ischool.berkeley.edu. And so this name server is actually authoritative for ischool.berkeley. And so it sends back the A record, including the IP address, which of course is what we wanted. I didn't draw it up in this tuple originally, but it also includes the TTL, and in this case, it sends 10,800, which is 3 hours. And so that's basically telling us we can use this IP address record for 3 hours. So that's how a lookup really works at the protocol level. Moving on, I thought we should talk about how a DNS domain name gets created in the first place. And so you can imagine maybe you just, created a company, Example Industries, and you get a block of IP addresses from your ISP, like maybe 192.0.2.0, and it's a /25. And so you go and register example.com with a registrar. And the biggest registrar, I think by a pretty large margin, is one called GoDaddy. And this is an organization that ICANN has delegated domain registration process to. And so registering example.com probably costs you less than like $15 a year. Actually, you can't register example.com. It has been sort of set aside to use for examples in networking things. But in theory, you register a domain name, it costs you about $15 a year. And then you run 2 authoritative name servers for your domain, or you have someone run them for you. I believe GoDaddy actually offers this as a service that you can pay for. Even like cheap web hosting plans will generally serve as your name servers for you. And you give the addresses of your name servers to the registrar. The registrar inserts a pair of records for those into the TLD name servers. And those are things like an NS record that says, for this domain, this is the name server that you should use. And then an A record telling what the actual IP address for that name server is. And so it would do that for both, or however many replicas you have. And then you put resource records in your name servers. For example, put an A record for www.example.com. And this costs you like basically nothing to create like as many subdomains as you want. It's your own server. You can just put in whatever records you want. So now, what if I want my own top level domain? What if I want my email address to be murphy@awesome.cs168? And to do that, you talk to ICANN. You can get your own top-level domain like CS168 for about $185,000. So kind of expensive in comparison, but people do this. If we look at the number of top-level domains over time, when they started selling more of them, originally they just had, like com and gov, and then all the country code ones and so on. But they started letting people sort of buy those top-level ones, and you can see when that happened, there was sort of an explosion of people buying them, though it's kind of leveled off over the last few years. So up until now, we've looked at the most essential aspect of DNS, which is resolving host names into IP addresses. In this segment, we'll look at some other use cases for DNS and dig into some of the record types that facilitate those. So to start out with, you might have multiple A records that have the same name. So here you can see that I'm using this tool called Dig, which does DNS queries. And when I query for yahoo.com, I actually get back a handful of A records. And every time I do it, they come back shuffled. This allows a sort of coarse-grained load spreading. Yahoo is running multiple servers, all serving their web page, and different users get a different list from the name server. And so if they just contact the first one, then different users get sent to different servers. This can also be used as a simple resiliency method. For example, if Google Chrome gets multiple A records and the first one doesn't work, it'll try the next one, and so on. You may have noticed that everything we've looked at so far has been focused on IP4 addresses. For IP6, you just use the AAAA record type instead of the A record type. And so here you can see I used dig to look up the A record for Google and got an IP4 address. And then I looked up the AAAA record and got an IP6 address. Now, another thing I might want to know is, assuming you've got an IP address, does it have a host name associated with it, and what is that? And this is facilitated by pointer records. And so the value stored in these records is the host name. The name part is a little bit trickier, the one that you actually look up. And so basically it's the .quad IP address listed backwards. So if I want to look up 138.110.1.200, then I start with 200.1.110.138, and then I append .inadder.arpa. And so here you can see I've done a query using dig for this IP address, and I put pointer at the end of the query to say that I want pointer records. And you can see that this particular IP address is associated with ns.mountholyoke.edu, which is Mount Holyoke's name server. There's a similar mechanism for IP version 6, where instead of adding inadder.arpa, you add ip6.arpa. We talked about how you can have multiple IP addresses associated with the same name by having multiple A records, and you can actually do sort of the opposite, where you have multiple names associated with the same A records. Or actually what's really happening is that you map from one name to a canonical name. And so essentially this is just creating aliases of a name. And this is done with the CNAME record type. So here you can see a query I ran using dig for www.berkeley.edu. And what I got back is this. And you can see here that it's a CNAME record. And basically, what this is saying is that www.berkeley.edu on the left should actually refer to this really long name on the right. And notice that the canonical name is actually an Amazon Web Services host name. So I guess we can conclude that Berkeley uses AWS to serve its main web page. Now, the next thing that you'd probably be interested in knowing is what the IP address for that AWS host name is, and it turns out that the server actually included it as an additional record and included the A record in the response, and that's what this head on the command line is about. I trimmed it off. So while the CNAME record type always maps to a single name, there's this similar record type called a DNAME, which maps like a whole part of the DNS tree to another part of the DNS tree. So, for example, if you try to look up something like blah.foo.com, it'll resolve it to blah.bar.com instead. So, another interesting use case for DNS is email. If you send an email to murphy@berkeley.edu, I end up reading it on google.com, right? And this is the same for all of you too, right? Since Berkeley outsources its email to Google. So how and why does this happen? I mean, how does it get to Google? If anything, based on what we just saw, you'd think maybe it would get to Amazon. Even in the past, it was really common to have a separate email server called something like mail.berkeley.edu, for example. But nobody wants to type an address for an email to murphy@mail.berkeley.edu. And so the way that this works is that when email servers are delivering mail, they look up an MX or mail exchanger record for the recipient domain. And this basically tells the mail servers to use that domain name instead. So if you look at Berkeley's MX records, it actually has several, and they all point to some Google machine. Another interesting type of record is the text record. Originally, these were meant for human readable information, but I don't think they were ever really used very much for that. More recently, they've been used for sort of a grab bag of things, but a pretty important one is for doing what's called site verification. So if we look at some of Berkeley's text records, you'll see several which mention verification. And the idea here is basically that some company like Adobe or Zoom or Google or Facebook gives you some magic value, and you put that in a text record on your domain. And then that proves that you have control over the domain, because not just anybody should be able to modify your domain's DNS records. The other company then unlocks capabilities for you regarding your domain. For example, Google has this feature called Search Console, and it'll let you see how often sites that you control show up in search results. And Facebook, you know how like when you share a link, it creates a preview with a title and a screenshot? If you're the owner of the site being linked to, then you can edit how those previews show up, but other people can't. The last record that I'll mention is the serve record. We already looked at the MX record, which was this sort of like special purpose redirection used for email, but what about other services besides email? Instead of having like every service need its own special record type, we have serve records. And so what you do is, if you want to connect to some service, then you look up this specially formatted name, where basically it starts with an underscore and then the service name. And then it has an underscore followed by the transport protocol name, like underscore TCP. And then it has the host name where you want to look up the service. The values for these records have a target host name to use instead of the one you looked up, similar to how we saw the MX record gave a different host name than the one we looked up for email. And the value also has a port number to use to contact the service. And this means we don't need to set aside a specific well-known port for every service, and we don't always need to use the same one. It can be looked up dynamically. So notice that it's like really easy to create more services. You just need to add a record with the appropriate name. You don't need to define a whole new record type and try to get it standardized or anything. There's another video where I dig into how and why serve records are used in Minecraft. And so putting aside record types for now, there's a million different ones, and we could go on about them all day. But let's talk about a sort of conceptual capability of DNS. That is, we've been talking about a lot of specific things that DNS does, but I want to take a little step back and look sort of at a way that it's used, and that's as sort of a general indirection layer. So starting with a really simple example, you might imagine you have some website and it maps to some address that was given to you by your provider. But imagine that you switch providers, and in order to not break aggregation, your new provider gives you a new address from their prefix. And if users were using these addresses directly, this would be a real pain, right? They'd need to like change all their bookmarks or remember a new address to type in or something. But with DNS, all you need to do is update the A record for www.example.com to the new IP address, and like most users will probably never even notice. And we can actually put this indirection mechanism to even more clever use. For example, maybe you run a company that provides video streaming and you have 3 servers with different IP addresses across the country. But you could use the same name for all 3 of those servers. And then we add a little brains to our DNS server. So when the server gets a request for that name, instead of just returning all 3 A records in shuffled order like we saw earlier for Yahoo, we could try to be a bit clever. So in the request, the IP address of the requester shows up in there. And we can use what's called a GeoIP database, which is essentially a mapping from IP address to their actual physical location. These aren't 100% accurate, but they usually get you within the area. And so we could have the DNS server return the A records ordered by which ones appear to be closest, rather than just a shuffled order. That's a pretty simplified version of this technique, and doing it well actually requires some subtlety, but this is like one of the underlying ideas behind a big business called content delivery networks. And there are lots of variations of this. For example, the smart DNS server may actively monitor server performance and direct clients to the least loaded ones instead of the physically closest ones. And so to sum up this segment, we've looked at a lot of things DNS can do. We've seen how having multiple A records for the same name can spread load across servers and provide some resiliency. We've seen how DNS accommodates IPv6. We've seen the mechanism by which DNS lets you map from an IP to a name instead of the usual way around. We've seen how we can have one name as an alias for another using CNAME records. We looked at how DNS relates to email. And we saw how site verification features are tied to DNS text records. And we glanced at a sort of general name-to-service mapping mechanism using serve records. And finally, we've looked at using DNS as a useful indirection layer in general. Okay, so I thought we'd do a little case study on DNS serve records in Minecraft. So as a reminder, we looked at MX records, which provide an indirection specifically for email. When you send an email to the address foo@example.com, the mail server looks up an MX record on example.com to figure out the actual email server where it should be sent, since the mail server probably isn't running directly on example.com itself. And that works great for email, but doesn't help us with other services. So rather than have a special record type for every possible service, the serve record was developed, which can be used for lots of services. In addition to a host name redirection like MX does, the serve record also lets you specify the port to connect to. So let's look at how this is used to solve a specific problem. So I imagine I don't need to tell you this, but Minecraft is a popular open world video game, and users can run their own server, which normally listens on TCP port 25565. Inside the game, a player can enter the address of a server to connect to, and this can be an IP address, but as we saw earlier, it's pretty cheap and easy to get a nice domain name, and people like to get ones that are memorable or funny. It's also the case that lots of people want their own Minecraft server, but they don't want to actually run it themselves. They don't want to use their home internet connection and their home computer, or pay for an expensive dedicated server in a data center or whatever. And so they pay a game hosting service to do it for them. And these hosting companies often want to run multiple games on the same physical server, since it probably doesn't take an entire machine to just host a few players. But if the server only has one IP address, all these nice host names people registered would all resolve to the same address. And this means you'd need to run the different games on different TCP ports, not the default Minecraft port number. So now other players would need to enter the domain name plus the port number, which is not nearly so nice. If you're going to have an arbitrary string of numbers in there, you might as well just be using the IP address probably. So a hosting company could assign many different IPs to the same physical server, which would solve this problem. You'd register your own host name and then create an A record pointing at one of those IPs and you'd be done. But IP4 addresses are a fairly precious commodity these days, so that's not really a great solution. And so the succinct problem statement here is that we want to run games that all have nice host names, but they all need to be able to refer to the same IP address with different ports. And serve records store exactly the necessary information. You create a serve record where the name is created by concatenating the service name and the transport protocol, and your nice domain name. And then the value in the record tells you the target server name and port number to connect to. The Minecraft code does exactly this for you automatically. So let's do an example. Let's consider two Minecraft servers, zerohub.dk and capsy.pw. And so I'll start by looking each of their A records up with dig. And we can see that this one actually has two A records. And next I'll try actually connecting to the IP addresses in the A records. I'm using a command line Minecraft client here instead of the actual game. And so this is just using the default Minecraft port number. And we can see that the first one doesn't work. And if I look at the second one, it doesn't work either. Fails in a different way, but they both fail. And so next I'll look up their serve records. And again, I create this special name where I put an underscore in the service name, Minecraft, and then an underscore and the transport protocol, which is TCP for Minecraft, and then the host name that I'm interested in. And here's the serve record. It's got the TCP port and domain name where the server is actually running. So I'll use this other tool called host to look up the IP address. It's really similar to dig, but has slightly more user-friendly output. And so here we see that the server is actually running at 88.99.151.100. I'll look up the other serve record for zerohub.dk. And again, we see the port number and the target domain name. And in this case, this is kind of illuminating because Infrequent Group is a Danish Minecraft hosting service. And again, I'll use host to look up the IP address. And the first thing to notice here is it says there's an alias. So this is a CNAME. And if we look at the A record, we'll notice that it's the exact same IP address as the other server. So they're running on the same physical machine, but different ports. And so now we can try connecting to one of these servers using the port number. And it works. And so here's one of them, and then we can kill that. Let's try connecting to the other one using its port number, 25573. And that works too. We get a different welcome message, presumably in Danish, because it's a different game. And again, the actual Minecraft game does all this for you automatically. So to tie this all up, this works by querying for a serve record that contains the name of the service that you're interested in. And the record that you get back tells you the host and port to actually connect to. And it's really easy to support different services. You just create more serve records. And so that's it for today. We will pick up talking about availability, scalability, and performance on Thursday.